Hello, everybody. My name is Mikolaj Pawlikowski. Everybody calls me Miko, so don't worry. And thank you for coming to my session. Two words about me. I am a software engineering lead at Bloomberg, running a team, running some managed Kubernetes. And I'm the author of a chaos engineering book by Manning, which is the topic of this session. So I'm going to claim that you, as SREs, and I expect to see a few at an SREcon, can't really afford anymore to not do chaos engineering. And I'm going to explain why I don't think it's a gimmick anymore and why you should be doing it. Every journey needs a plan. Here's one for the next 40 minutes. I'm going to start by defining what chaos engineering is so that we are all on the same page. I'm also going to go into what chaos engineering isn't, because it's equally important and there's just a lot of myths that are floating around, and I would like to debunk some of them. Once we're done with that, I'm going to do a few quick demos just to give you the feel and, to check the technical presentation check mark on this. And then we're going to cover a few things about starting. I assume that, unless you have lived under a proverbial SRE rock, you have heard of chaos engineering, and there might be reasons why you haven't adopted that, or might be reasons why you have adopted that, and you would like some pointers on how getting started can be easier. So we'll do some of that. Then I'm also going to very quickly go through the tools, including chaos engineering for people. That's kind of like a nice aspect. We'll cover that. And then I'm going to shamelessly plug about my book and invite you to connect. If that sounds like a reasonable plan to you, let's do it. So, starting with chaos engineering. Okay, all right, yeah. So this principles of chaos.org is where you can find what I consider a canonical definition of chaos engineering. Chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. If we remove just the fluff portion of that sentence, we're left with experimenting to build confidence to withstand turbulent conditions, right? So we've got the turbulent conditions. That's the failure that we will be injecting to most of the time the failure will be injecting to a system. But at the core of it, it's very simple. It's experimenting on something, a system, to just be more certain, more confident rather, that the system behaves the way we expect it to behave, right? There's nothing more that you can do, nothing more practical you can do than go and verify that experimentally, okay? So there is it, that's it. There is no chaos monkeys in it, there is no massive distributed systems. That's it, experimenting. Experiment should also bring science to you, and that's kind of like an aspect that I'm kind of trying to propagate, that we really want to be scientific about that, and we want to know what we're doing. Okay, so definition is cool, but what we really care about with all of that is the reliability, right? Well, rings a bell. Pretty much everybody calling themselves SRE is going to know that what we're really after is reliability, right? You can define it, you can slice it, dice it, but we want to have some kind of fulfillment of the reliability aspect, okay? So this is where chaos engineering and the SRE kind of come together. It wouldn't be a real presentation if there wasn't a Venn diagram, so let's check this box too. We have the SRE, chaos engineering, and hopefully some overlap, right? I'm going to argue that this overlap is pretty significant, and for some, probably looks more like this, where the chaos engineering is a kind of like a subset of SRE, a tool, methodology that you want, that you can use to achieve your SRE goals. One little problem with this kind of representation is that, it gives this impression potentially that it only applies to the site reliability, like the platform level, and it doesn't necessarily work for the application and front end stuff. I'm going to argue that this is not true. I'm going to argue that it also applies pretty much to any system, any size, any shape, and works very well on the front end too. An example of that being a chapter, one of the last chapters in my book, where we actually go and we inject some JavaScript into a front-end code to verify that the failure that we expect to see in real life is actually handled the way that we think it's going to be handled. So regardless of whether you see this circles kind of more spread out or whether you feel like the overlap is massive, there is something, right? And so we went from basically like a fun blog post a few years ago, coming from Netflix with the Chaos Monkey, to a point where we're trying to apply this more seriously, kind of more scientific record, which doesn't mean that the myths are just magically going to go away and resolve themselves. And this is like my top 5. This is stuff that I pretty much hear daily, right? So first thing, when I mention chaos engineering to people, it's like, oh yeah, Chaos Monkey. It's Chaos Monkey, right? Well, yeah, it initially was Chaos Monkey, and that's where it came from, but we've come a long way already. And, kind of like detaching yourself from just this randomly smashing things in a cloud environment for a company like Netflix and going towards more scientific approach is something that, I'm trying to propagate with my book. So it's not just Chaos Monkey. It's much more than that these days. And that's myth number 1. Another one is kind of interesting because it is kind of this unique aspect of chaos engineering that tends to be pushed to the headlines when you read a blog or a video. It's the testing in production. And it's a funny one because, obviously, when you release software, you don't release it directly to production. You do your testing, and then on top of that, you release through whatever QA stages that you have, whatever your process is. It would be reckless to just go and release something directly to production. Depending on where you are, obviously there are different things. There's different deployment models. You can do percentages. You can do a lot of things. And all of that applies exactly the same way to chaos engineering. There's no like a magic pass when you say, oh yeah, well, I'm doing chaos engineering, so I am now permitted to just run this experiment directly in prod. The same principles, best practices, all of that applies exactly the same way. The twist with chaos engineering is that the holy grail is to kind of test in all of your environments. And the reason for that is that, by definition, obviously, all the testing that you do that isn't in production isn't going to be perfect, right? It's going to be an approximation. All of the previous stages that we build, we try to approximate the production environment as much as we can, but when you think about it, by definition, that means that you can't really test things properly because in production, the things will be slightly different. The data will be different. There is going to be different usage patterns. Obviously, we could try to approximate all of these things, but at some point you have to draw a line and just say, okay, yeah, all of that is an approximation. Might be good enough, but it's never perfect, right? So the holy grail of doing chaos engineering would be that you're so confident in your system that in all previous environments, all of the failures that you introduce in that are automatically handled. It's transparent, everything's behaving the way you want. And you're so confident to the point that you actually go and do the same thing in production. And, it's obviously a fun topic because it's kind of counterintuitive. There is going to be situations when that doesn't fly, right? If you can't afford to have any extra failure that you wouldn't otherwise have, if lives depend on that, probably not going to fly. But there's plenty of scenarios where it's better for you to even potentially break some percentage of your user traffic just because this way you can detect the failure, the problem earlier. And it's also good for SREs because, hey, they're in the office. They're doing this on purpose, so no one has to go and wake up and log in and debug and try to do all those things. If it breaks while we're looking at it and we expect it to potentially break, that's great, right? So production, funny topic. Another is one for number 3 myth for my top 5. it's only for massively distributed systems. Well, yeah, sure. It works nicely for massively distributed systems. If you have a massively distributed system and you could have a use case like that, that's great. Makes for nice presentations. But one of the reasons why I wrote the book about chaos engineering is that the same principles can be applied to systems of any size and shape. It doesn't have to be massive. It doesn't have to be a microservice platform. It doesn't have to be any of those things. One of the things that I'm going to show you in a minute is that you can take like a single process and you can apply chaos engineering to verify that it's behaving the way that you want it to behave, well, that you expect it to behave, rather, with an experiment, right? So kind of like a parallel to that is like it only works on insert the technology here. Well, it only works on Node.js or Golang or Rust or whatever. No, it's a methodology. It's a mindset. It's a thing that works on whatever you throw at it, and all of the kind of technologies, frameworks, and platforms and whatnot is are secondary. And you just apply the same principles to verify that the systems that you build, at the end of the day, these are all just tools to build whatever we set out to build, behave the way that you want it to. And finally, like the breaking things in randomly thing is, it kind of goes back to Chaos Monkey, right? The first thing that people saw was Chaos Monkey, and it was randomly breaking things. That's cool. And it's definitely part of the chaos engineering game, but it's just one aspect. This is very good when you don't know where to start, when you set out to potentially break your system and find things. Like if you just run this randomly, you can probably detect a lot of things. The more complex your system is, the more spectrum, the more surface there is for failure. If you have this, big system and you have a microservices and you have all this surface for things that can go wrong, running things randomly is kind of like fuzzing, right? It's kind of like similar aspect that you just generate this random situations, random inputs, and you see what happens. And more often than not, you're going to discover some things, some race conditions, some interesting emerging properties of the systems that you didn't think about or didn't design the thing for in the first place. But this is just like one aspect. Once you get a good understanding of how the system is supposed to work, you can design and tightly control the variables in your experiment. The problem with that is that you discover something randomly, and you might not have the observability set up for that. You might not know how to debug that. You might discover, oh, there was an error, but because we didn't expect that kind of error, we're going to have to try to rerun it to actually find out what happened exactly. But like a lot of the work, personally from my experience, is about designing this tightly controlled, very scientific, very, not fun, very boring experiments where you test a very specific, isolated part, behavior rather, of the system, just to make sure that it aligns with what you expect to see. Okay, so this aspect from like the cool thinking, breaking things random in production, chaos monkey stuff, towards the scientific approach is what I've been trying to push with my new book. And it kind of boils down to 4 steps to an experiment. First thing you need to do is you need to be able to observe what's actually happening. That's what we call observability in this context. It's basically picking some set of variables that you're going to be able to reliably measure, okay? Because if you can't measure them, you're just kind of guessing, right? But if you start with defining these variables, it can be anything. It can be throughput of your service. It can be a throughput writing to disk. It can be something very low level, or it can be something very high level, like success rate for your user or your API. Whatever it is, it needs to be reliably measured so that all of that makes sense, right? Then the second step is defining the steady state. And the steady state thing sounds academic, but What I really mean by that is just the normal range of that variable, right? If you need to know where your starting point is. If you are looking at the throughput of your service, it doesn't make any sense to run an experiment if you don't know what the typical throughput of that service is, right? You need to know what's normal and what isn't normal. And typically, once you've defined a variable and you've found a reliable way of measuring that, finding this normal range for the variable, the steady state, is actually pretty straightforward, obviously, with exceptions. And then the third point is where when things start getting interesting. That's what coming up with a hypothesis is. And the hypothesis is usually in the form, when X happens, this is what the variable should behave like. Okay, so for example, I know if we have a service, we talk about requests per second, and behind the scenes, we're interested in knowing what's actually happening when we lose one of the servers. Is it like retried? Is it transparent to the user? Does the user see the expected drop in the speed? Do they see any reduction in the speed at which they can go in terms of requests per second? All of these things that needs to be defined, right? And looking at your system, the way that you design it for, you give it these characteristics that you expect to be true, right? You want this to happen. That's why you design it this way. And then with the chaos experiment, you write this hypothesis, you come up with this hypothesis to verify that what you did is actually working, right? And then number 4 is just run the experiment. And it's implicitly you run the experiment and, analyze the results. And I was kind of tempted to add the 5th step, analyze, but in marketing says that 4 steps is a little bit more attractive, easier to remember. So basically, bottom line, and I keep hammering this point home, is that we're trying to take this from this fun gimmick to a more serious, scientific, let's put our lab coats on and protective glasses and gloves before we do this kind of thing scenario, to make it basically useful and make it a tool for everybody, and specifically, this crowd, the SRE crowd. Okay, so let's go and take a look at some things. I wanted to really drive this point home about this applying to different systems. I'm going to do 2 demos, and with the kind of online thing, hopefully they work out both times. One demo is going to be about a smaller system that I could come up with and apply some chaos engineering to it to show you. And it comes directly from a book, and the other one for a little bit more complicated of a scenario. So let's just switch and do that. Demo number 1. This is coming directly from my book, chapter 6. And this is a VM that ships with the book. So if you want to follow, the examples, you can download it from GitHub, and it ships Ubuntu and all the things pre-installed and all the examples too. So what I'm going to demo now is that even the most simple example of a system I could think of, a single process running on a thing, on a server, can actually benefit from chaos engineering. This is a legacy server. It's as legacy as it gets. No one really knows how it works. No one even knows how it's built. All we know is that we have this binary called legacy server. It's 49K, not very big. And what we can do is that we can start it. It claims to be running on port 8080. Let's go ahead and verify that. Let's go to Firefox 8080. Check if it's actually accessible, and looks like it is. And well, that gives you a hint of what it's actually doing. Let's close this. And so we're going to be interested in knowing what happens when this thing breaks, when it stops working the way you expect it. Yeah, now it's worked fine. But what happens if it can't do the most basic things that it's supposed to be doing, like a write syscall? And the chapter goes into the details of all of that to help you with this, but I'm just going to go and show you some visibility. So I'm running Apache Bench. with concurrency of 1 for 10 seconds to localhost 8080. It's going to complete some requests, and then my observability is going to be based on this. Complete requests, 17,000. Failed requests, 0. Total transferred, all of that. So we are looking at 1,700 requests per second, and all of them are successful. Okay, so this is great, right? But what happens now if it wouldn't be a shame if your server couldn't write? And this is where we can use SREs to do that. So this is a snippet. I didn't just come up with this. It's coming from the chapter. We're running SREs on a process with PID of legacy server, the one that we just started. We could just copy paste the PID. We're going to want a summary with $C, and we're injecting errors. So we inject a write syscall error, and we're going to return an error IO instead of whatever it would return. And we're also going to use a little unknown feature of SREs injection that we're only going to apply this to every other call. So this snippet basically is going to attach to SREs, to our legacy server via SREs, and it's going to inject failure. So let's go ahead and do that. Process attached, 4754, 4754, all is good. So let's see now what happens if I rerun my hypothesis implementation. We're going to rerun the 10 seconds worth of requests, and let's see what happens. What do you expect to happen? We just blocked every other syscall doing right, and whoa, what's that? It looks like the fail requests are still 0. Complete requests, on the other hand, are much slower, and this is a problem with SREs, that the performance goes out of the window. So, remember about that, go much more into the details. But look here, what's actually you can observe here is that it's trying to write all those characters to the client, and then it gets the error injected, just like we expected, right? The problem, though, is that it actually can't do that, right? It gets the injected error. The good news, though, is that it seems to be retrying every single one of those writes, and so because of the fact that we did every other write that's failing, it's actually eventually succeeding. So some of the penalty from the time is going to be because of this retries, and some is going to be just because of the SREs. So what we did here is that with one command, we injected failure into a binary that no one really knows what's doing. We didn't even look at the source code. And yet we have been able to experimentally verify that despite that, it's actually still succeeding. So we know now that if every other write fails, it still retries successfully. Okay. That's for demo 1. Let's take a look at the other demo. Okay, for the second demo, we're going to go to the other side of the spectrum. Instead of going for the simple, we're going to go for the complicated. So what I've got here is a Minikube setup. I have got a Kubernetes cluster running on my laptop here with some pods running in it. Of particular interest is the Goldfinger pod, the 3 of them. Goldfinger, another shameless plug on my side, is a project that I wrote that's available on GitHub too. That basically came from the need of detecting when we had issues between nodes in our cluster. So typically with Goldfinger, you run an instance of Goldfinger per node. So every node is going to get an instance, and then the Goldfinger instances ping each other to produce a complete graph of connectivity. And then it allows you to detect things, detect errors, slowness, and all kinds of issues that you might have connecting between the pods. So I'm running the Goldfinger route right now here. Let me just quickly start Minikube service Goldfinger to show you the UI. Copy, paste that for you. So this is what the UI looks like. It shows you live the three graphs and the three nodes on the graph. You can refresh that. An interesting thing is that you have also the heat map here that you can color differently based on the time it takes for the things to connect between each other. So warning threshold for me is 5 milliseconds here because this is all running locally. And the problem threshold is at 100 milliseconds. Okay, so what we're going to do is we're going to use Powerful Seal, which is another project I mentioned earlier that allows you to run sophisticated chaos engineering experiments on Kubernetes. And I've got here an experiment that I wrote for you. And you don't really need to know much about it. You can kind of read, this is YAML, this is what scenarios for Powerful Seal look like. And in this particular one, it uses the clone functionality. That's kind of new to it. So instead of modifying existing software so that we minimize the blast radius, it's going to clone a deployment for me, the Goldfinger one, and with 2 replicas, and it's actually going to mutate it. So instead of just copying like as is, it's going to inject a toxic proxy toxic with a latency on the port 8080, that's the Goldfinger port, and it's going to run the latency of 200 milliseconds. So the way you run this kind of thing is you just run seal autonomous policy file experiment name, and you can see here that it started the scenario, did the clone, and it's now sleeping for 120 milliseconds for 2 minutes. And if we look back at our pods now, you can see that there are now this additional Goldfinger chaos pods. If I go back to the UI and I reload, let's just give it a few seconds to actually start so that the graph is full. By default, Goldfingers ping each other every 30 seconds. So when it comes up, it might not be able to do it. So you're going to wait the 30 seconds max to get that. So now I have the full graph. I have the 2 chaos ones and the 3 remaining ones. What you can't see is the latency unless you go to the heat map. And boom, you can see here that these chaos nodes are receiving latency. The 2 green squares here represent the fact that by default, the toxic proxy doesn't apply to localhost. It only applies to the incoming connections. And you can see that the pods here are experiencing over 100 milliseconds threshold. If you want to actually go and see the details, you can just click on it, and you will see we should see the delays over 200 milliseconds, 250 milliseconds, 252 in particular here. At the end of the experiment, it's just going to clean up after itself. I didn't add any validation here. You can also do that with Powerful Seal to actually issue some requests and verify that things are working. But the nice thing about it is that we haven't actually touched any of the critical path. We just added extra pods, and these pods got the latency added to them. And also, we actually didn't have to write any low-level code. We just literally told Powerful Seal to implement this experiment for us. And you can see here, all done here, cleanup done. If we go back to the pods, they are gone. And if we reload, eventually the chaos pods will go away too. Okie dokie. So that wraps up the other demo. And let's jump back to the slides. All right, so that's it for the demos. The next question is, okay, so demos were cool. I am convinced. I would like now to go and apply that. And because of the myths, I am encountering some friction. And this is like a typical scenario, when I first introduced that, and, I'm kind of wishing that it was given a slightly different name rather than chaos engineering, because it's really confusing people. But hey, it is what it is that you have these 2 conversations. You want to generate this buy-in, and you have the 2 parties. Typically, you have your team who just wants to be called less, right? They want to have less drama. And this kind of goes back to the point that I was making when we were talking about the myths, is that, yeah, when we do in this chaos engineering, even if we break things, we break them kind of on purpose. We break them during working hours, and nobody gets called. And then after we gain this confidence that this is running well, and these are all the failure scenarios that we've tested, you really do sleep better at night. And by the way, this is kind of like how I ended up doing this chaos engineering thing to begin with, before I realized it was supposed to be called chaos engineering, is that I was working on this project that adopted Kubernetes. And I think 2016, I was version like 1.2 or something, and it wasn't stable. I mean, patches were coming in quicker than we were able to apply them. There was no really good way of knowing what's the best practice to deploy those things. It's much easier to deploy them today. So the one thing that we could come up with was to try to apply this kind of random scenarios that we expect to break, and see whether the setup survives that. And that eventually ended up being the, called chaos engineering, and we're still doing it to that day. So that's kind of just, sorry, a little side note there. Buyin. So when you do talk eventually to your manager or your boss or whoever, they're going to have some questions like, hey, okay, well, one of the things you're going to hear, apart from the myths there, and that I've covered already, is like, okay, don't we have chaos already? Yeah, we have chaos at home. And so the answer to that is that you need to have a conversation about the risk and reward. And humans, from like the evolutionary perspective, with all this baggage that we've accumulated, tend to be pretty terrible at estimating risks. An example of that, you've probably been wondering why there is a shark on the slide there, is that if you ask anyone in the street how likely they are to be killed by a shark, they're going to probably overestimate that by a lot. And that's because they watch the movie Jaws, and they're afraid of sharks because they, clearly eat people all the time. Or, probably a more modern equivalent, the Meg, for Jason Statham. But when you actually look at the numbers, this is not what's killing people. If you are an American who died last year, chances are that it was the heart disease or cancer that got you, right? Heart disease is killing over 600,000 Americans each year. And yet, people are not that scared of that burger. Hey, that burger doesn't scare me at all. What scares me is this sharp teeth and this massive shark that's, going to actually go and eat me. So before we put any numbers to these things, before we go and do a little bit of back of the napkin calculation, a little bit of math like that, it's really hard to narrow down. And the good news is that once you do put some numbers on the back of a napkin, it's much easier. And even if these numbers are really rough, and even if they're off by a factor, you can still have a much easier time convincing people. Okay. Another thing that I found very efficient at generating some of the buy-in is the chaos engineering for people aspect of this entire thing. And if you're interested in that, I have a chapter. I think the last chapter in my book, number 13, is about people, and it's about looking at human systems, aka teams, and realizing that they're actually very similar to how we design the computer systems. And this aha kind of moment came from a talk given by Dave Renson from Google that I really liked. And it's both a tool that you can apply to improve your system's resiliency, your team's resiliency, detect things like bottlenecks and inject a little bit of failure. Say, for example, ask a person to be slow or ask a person to not give any information and see where the single point of failures are and how the team actually works. But it's also a really nice thing that you can discuss when you get into buy-in, because it talks about people, and your manager is going to spend a lot of time trying to understand the dynamics between people. And if you start with that, they might have this aha moment, and then you're going to have a much easier time try to convince them that you should be doing more chaos engineering. Okay, well, we could talk about that a lot, but I'm running out of time, so I'm going to jump ahead and do the next step. So we've talked about chaos engineering, what it is, what it isn't, what it's supposed to be, how to apply that, and how to get a buy-in. The next step is obviously to go and get some tools. And the good news is that a lot of these tools are actually, have been there forever, and we're just reusing them in this context. If you want to take a look at tools that are more specifically designed for chaos engineering, here's a little selection. From the top, Powerful Seal, full disclosure, I wrote that. It's a tool for Kubernetes chaos engineering, pretty neat. Chaos Toolkit, another very neat framework that you can use, a bit more generic than just Kubernetes. Pumbaa, chaos engineering for Docker containers, makes it much easier to implement some of your experiments. Proxy, that's the monkey there with the banana. It's a kind of general purpose proxy that you can program, and you can generate failure, slowness in different routes. So you can stick it in between two components in your system and then inject like throttling, inject failure, inject stuff like that, and verify that your system behaves the way you want it to. Really useful. Chaos Monkey probably doesn't necessarily need an introduction. Then I also put a Byteman here, and this is a very neat tool that allows you to do on-the-fly code injection into the JVM. So you can do things like, without modifying the source code, you can trigger exceptions in your Java code or whatever is running your JVM code, and verify that the system as a whole behaves that way in a real setting rather than just unit test. Right, and the last one, the one here that I'm kind of covering, that's a nice party trick. Kube Doom basically plays Doom, and you can kill pods in your Kubernetes cluster by shooting them. If you need more, well, you're probably going to need more. I recommend the awesome Chaos Engineering, the one with the link here. It's a nice, awesome list that has a lot of different tools, materials, videos, books, and so on. Really good stuff. Finally, time for my plug. This is what the book looks like. Site Reliability Through Controlled Disruption is the subtitle. It's available from Manning. So manning.com/book/chaos engineering. It's currently only available online. It should reach print by the end of the year. Hopefully, that's going to be my Christmas present. And like I mentioned, it covers a lot of surface. It tries to be a technical book more than theory book. So you have the portion about the theory and the motivations for chaos engineering. And then I go and cover different layers from like the thing that we just saw, blocking syscalls to verify a single binary, through covering Docker and how it works under the hood, how to do chaos engineering, JVM, browser stuff with JavaScript, application layer when you inject it directly into your application code, all the way to Kubernetes, how Kubernetes works, how to verify your Kubernetes actually works, and how to do chaos engineering on the stuff that runs on top of Kubernetes. So if you like the book and you would like to reach out to me, scan this QR code. This should be pretty neat, and it should take you to my LinkedIn profile, which is probably the easiest way to reach me right now. These are the photo credits, for example, with the amazing shark. And finally, we are hiring. So if you like the sound of this, go to bloomberg.com/career and reach out to us. We're looking for people who are excited about reliability. We're looking for great software engineers. And if you would like to join us, we'll be delighted. And with that, thank you very much, and enjoy and stay safe.